Earlier in the morning, I introduced Theorem 2. Okay, I just want to emphasize in shortcut form what Theorem 2 says. Okay, if you have got an angle at the center, okay, and an angle at the circumference, right? If those two angles are subtended by the same arc or same chord, we can conclude that the angle at the center is 2 times the angle at the circumference. Okay? So, if you have got a diagram like this one here, let me use the big one. If this angle here is 2x, okay, that angle there is going to be x. Right? Why? Because both angles are subtended by the same chord. And that chord is going to be called AB or arc AB. Is that clear to everyone? Okay, so the angle at the center is 2 times the angle at the circumference if both angles are subtended by the same arc. Okay, this angle here must be at the circumference. It has to be at the circumference. If it's inside the circle, then the theorem is invalid. So one angle must be at the center, other one must be at the circumference, and both angles must be subtended by the same chord or same arc. Okay? And the shortcut form for that theorem is angle at the center is equal to 2 times angle at the circumference. That's the shortcut form. You don't have to write a full sentence. Okay? Now, the proof of this theorem is examinable. The proof is examinable. So, to do the proof, let's use diagram 1. Okay? To do the proof, let's use diagram 1. So, let me make some changes to the one that I made. So, forget about diagram 2, let's use diagram 1. Okay? So, what we do to diagram 1 is this point here is the center. So, we label it there. Okay? That point there is the center. Please take note of that. So, we join CO and produce it. Okay? By produce means we draw a line beyond point O. So, we draw a line like that. Okay? That line is going to create 2 angles here. Okay? One of them I can call it O1, the other one I can call it O2. So, once you produce that angle there, we can end up having we'll end up having 2 angles here. So we can end up having C1 and what? And C2. So that we can say O1 is equal to C1 plus A. So which means this angle here, I can call it O1. So let me use a different color. My pen is giving me problems. Alright. Let me rectify that. Okay, let me use this color. Blue is not a good one. So let me use green. So this angle here, I can call it O1. That one I'll call it what? O2. At the same time, I can also call this angle inside this triangle, I can call it C1 and that one C2. These 2 angles, C1 and C2, are formed by constructing a line from point C passing through the center and going beyond the center. Okay? Now, why do you do that construction? It's because it's part of the proof of the theorem, because we know the exterior angle of a triangle theorem from grade 8, and I told you about it on Monday. That's one of the theorems we use here. So, O1 is going to be equal to C1 plus angle A. That is in triangle AOC. Remember, I did the exterior angle of a triangle theorem, and I refreshed you on Monday if you were here. So angle O1 is going to be equal to C1 plus angle A. And the reason is that it's because of exterior angle of a triangle theorem. Okay? Then, now you need to be aware that CO is a radius. OA is a radius and OB is also a radius. So we have got 3 radii. So I can write here now, OA is equal to OC. Okay? They are radii of a circle. So all radii are what? Are are equal. Okay, then once I write this that OA is equal to OC, this is OC, that's OA. I can therefore say that angle A is equal to C1. The reason that you give there is not isosceles triangle, it's angles opposite equal sides. Okay? This will be the reason that you give. If you want to prove that two angles are equal based on their opposite sides, the reason that you give for any triangle is angles opposite equal sides. Okay? That's what is required based on examination guidelines. And this reason here is a common reason which appears in examinations or in questions on geometry. Okay? So if you prove that two angles are equal in any triangle, the reason that you must give is angles opposite equal sides. Yes? At the bottom here. Okay, so I'm here. Right? Then you also need to be aware that O1, this angle here, is going to be equal to 2 times C1. Now, why? It's because, you see, what we have there of saying C1 is equal to A. This is the angle here. If C1 is equal to A, do you agree with me that this angle here is going to be equal to C1? Do you agree with me on that? Because of this statement. Which means I can replace angle A by what? By C1. Because of that, you can end up having O1 being equal to C1 plus C1, which gives you what? 2C1. Right. Please ask a question based on, because it can be a tricky part of the proof. Alright, firstly, we proved, or rather, it's actually from your grade 8, right? This angle here, it's an exterior angle of triangle AOC. An exterior angle of any triangle is equal to the sum of the two interior opposite angles. So O1 is equal to C1 plus angle A. That's what we have in this step here. You get that? Now, at the same time, because OA is a radius and OC is a radius, it means that the length of OC and OA are equal. Therefore, triangle A into triangle AOC, you can call it isosceles in course, right? Hence, angle C1 is going to be equal to angle A because they are angles opposite equal sides. Therefore, you see where there is A here, I can put C1 there, here. So that I'll end up having O1 is equal to C1 plus C1. And that will give me angle O1 is equal to 2C1. That's what we have here. Okay? Then, similarly, we can do it on the other side. Angle O2 is equal to C2 plus B. Okay? So, and again, O2 is going to be equal to 2C2. Okay? We carry on. So we end up getting that. The reason is because side OC or length OC is a radius and OB is also what? A radius. Therefore, C2 is equal to angle B. Okay, so we can come up with another equation which will be that one. So this equation here, O2 equal to 2C2 and O1 equal to 2C2. We combine those two equations. We add the left-hand side separately and the right-hand side separately. And we equate those sums. So once we do that, we end up getting a new equation. O1 equals O2 is equal to 2C1 plus 2C2. What happened here is we added the left-hand side here and the left-hand side here. Also added the right-hand side here and the right-hand side, and we end up in one equation, which is O1 plus O2 equal to 2C1 plus 2C2. Then you take out a common factor on the right. Once you take out a common factor now, you need to be aware that C1 plus C2 is the same as angle ACB. ACB. And then O1 plus O2 is the same as angle AOB. Okay? So we end up with AOB is about 2CB. That's the proof of the second theorem. Okay? This proof is examinable. Okay? And the application of that proof is one of the easiest in circular geometry. I'm going to do some examples just now. Okay? Any question? Yes?
So the question is asking to join CO and produce.
Yeah.
What do they mean by and produce?
Produce means draw a straight line beyond that specific point. So if you draw a straight line, if you join OC, you start by drawing the line from point C. You go to point O, but you carry on going down. That's what it means by produce. Okay? It's not a diameter. Because you see, I didn't go as far as the circumference. I just stopped just before the circumference. So you cannot call it a diameter. Alright? So let's do some examples. In fact, let me introduce Theorem 3. Then we move on to examples. Theorem 3 is related to Theorem 2. So Theorem 3 is also one of the easiest. Theorem 3. Okay. Theorem 3 says the angle subtended by, the angle subtended at the circle, that is the circumference, by a diameter is a right angle. Okay. So an angle which is subtended by diameter at the circumference is always equal to 90 degrees. Okay? The angle subtended at the circle by the diameter is equal to a right angle. Right? Now, generally, the shortcut for the reason, we write it as this. We write this angle in semicircle. That's the shortcut. Angle in a semicircle. So whenever you see a diameter and there's an angle subtended at the circumference by that diameter, the reason that you must give this angle in a semicircle. Okay? Whenever you see a diameter, first you see that there's a diameter and there's an angle subtended by the diameter, then it means you are supposed to use Theorem 3. Angle in a semicircle. Okay? So here, you look at this, the first circle, AB is the diameter, and we have got angle C here. This angle here is going to be equal to 90 degrees. Because it is subtended by what? By AB. And it comes from Theorem 2. Okay? How does it come from Theorem 2? Do you agree with me that if AB is the straight line and it's the diameter, the angle here is going to be equal to 180 degrees. So angle at the center is 2 times the angle at the what? Circumference. Therefore, half of 180 is what? 90 degrees. Alright? So that's your Theorem 3. Right? Now, Theorem 3 also has what is called the converse. Right? Remember, I told that a converse is just a statement that is the opposite of another statement. Okay? So, the opposite of that is that if you've got a chord that subtends an angle at the circumference and that angle is 90 degrees, you can conclude that that chord is a diameter. Okay? If a chord subtends an angle which is equal to 90 degrees at the circumference, it therefore means that the chord is a diameter. So the shortcut for that, well, sometimes we get a question saying prove that this line is a diameter. Okay? So your reason will be chord subtends 90 degrees. Or you can say converse angle in a semicircle. There are two reasons there. Or you can write it as converse angle is the opposite of the original one. Angle in a semicircle. That's another acceptable reason. Okay. The two are related. All right? Any questions before I go? Let's see how we can apply some of these theorems.